Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at sampling distributions and the Central Limit Theorem. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to be joined tonight by our two panelists, Diane Broberg and Jeff McCullough. Diane has been teaching high school math for 25 years. She served on writing teams for Texas Instruments and taught many summer workshops. Making math come alive for teachers and students keeps her creative. Outside of math, she's an avid runner. Diane, thanks so much for being with us tonight.
I'm glad to be here.
And Jeff co-founded the TI-Nspire Super User Group with Bryson Perry. He teaches Algebra 2 and AP Statistics at St. Mary's Episcopal School in Memphis, Tennessee. In 2009, Jeff received the Presidential Award for Excellence in Mathematics and Science Teaching, and he also authored the second edition of the TI-Nspire for Dummies book, as well as the second edition of the TI-D4 for Dummies book. Jeff, thanks for being with us tonight.
Hey, it's good to be here. I also am a runner, but I just try at running. It's a little different for me.
So you try, and Diane's actually a runner?
Yes, she's the real thing. I've run with her before.
Thanks for clearing that up. We're expecting a large crowd tonight, so your audio is muted. Feel free anytime to send any questions to Diane or Jeff using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'd love for you to follow along. The best way to do that is at your own pace, which means that you're going to wait a couple days for the recording to become available in your email. It'll automatically be an email that will be generated and sent to you. And with that recording, again, go at your own pace. You can pause, rewind, and really take whatever time is necessary to digest everything that's going to be happening tonight. We hope you don't have any audio issues, but in the event that you do, try finding in the participant window with your name, there's going to be an icon that looks like a phone. By clicking that icon, you'll receive call-in information, and you can switch from the default audio broadcast to actually using a phone, which should clear up any further potential audio issues. At this point, Jeff is going to discuss our agenda. So
we're going to be looking at a problem today, making sense of the Central Limit Theorem. I'm proud of that name, although I'm sure I took it from someone else. But it's an activity with pennies that we're going to talk about. And we're going to talk about the sampling distribution of sample means, what that means, how we teach students that concept. And we're going to approach it from two different ways. One is the TI-Nspire, and breakthrough for both of us, we figured out a way to do the same kind of thing on TI-D4. And so that was a real exciting time for us. We're going to share that with you during this hour. And also, we'll talk about the Central Limit Theorem. And on Math-Nspire, there's actually a document that we'll talk about. And then also, some AP stats problem, if some of you maybe teach that, or even if you don't, I think you might be interested to see what kinds of basic questions about the Central Limit Theorem there might be there that we can look at. And of course, I love getting free stuff, and there's an opportunity for you to win a free registration for two to the international conference that's coming up.
Thanks so much, Jeff. And Diane is going to discuss our expected outcomes.
We're hoping by the time we're done with this session tonight, you'll be able to both create and display sample distributions. It doesn't matter which technology you've used. If you use the 84 or the Nspire, you'll be able to do that in your classroom. We're going to actually show you some activities that you can use to help students discover these, and we hope that they're activities that you can then take back, and if you want to, you can use them tomorrow or you can use them next year. And then we're going to do a variety of things with both technologies that calculate probabilities and using the normal distribution. And as Jeff said, we're going to talk about a couple questions that come from the AP where students actually use this in their testing situation.
Diane, thanks so much. Jeff, it's all yours. Feel free to share your screen.
Sounds good. Okay, So this is an activity that I've done with my students in my classroom. And oftentimes with math, not just stats, but maybe especially stats, I think it's a good idea to, when you can with math, to start with a hands-on activity rather than just going straight to the calculator, straight to crunching the numbers. Diane, do you do something similar in your class? Do you ever start with like a hands-on activity when you just taught Central Limit Theorem in your classroom, correct?
Yep, and we spent a lot of time collecting data. I think that's one of the most important things we can do is collect data and to actually have students physically deal with it as much as they possibly can.
Yeah. So this one took a little bit more prep than some things I've done in my classroom. They actually had to bring pennies from home. I encouraged them to bring just pennies they found in a jar or under the couch cushions or wherever, because I didn't want them to get penny rolls because I thought they might be just all super recent pennies, like 2018s, 2017. And so they each brought in a whole bunch of pennies, and I actually took a picture of them. We organized them by age. And so the way we did the ages is a 2018 penny, we considered that a year old, which is probably true. Don't you think? Is it like cars? Don't they come out with pennies a little bit early?
I assume so.
I assume so. And it worked better. I like starting with 1 rather than 0 for this activity. So 2018 pennies, you see we have a bunch of those. A real tall tower of right there of all the 2018s and then 2017s, 2016s, and so forth. And we had some that were 50, 60 years old out here that kids had just found, and they might have been. I'm not sure where the Indian head pennies came in, but they're getting pretty old there. And so, Diane, this was our population. So I know there are more pennies out there, but we considered this our population of pennies that we were going to draw from. How would you describe this population in your words? What do you think, Diane?
If I'm talking about it, I'm going to say it's pretty skewed.
Skewed which direction?
Oh, I think it's probably skewed to the right.
Yeah.
And,
okay.
My guess is the mean's got to be pretty close to the left-hand side somewhere. I can't see the little numbers down there, but the mean's got to be pretty small.
Yeah, maybe somewhere in here, 15 years or so.
Yeah, something like that.
Not sure exactly. So the interesting thing about this data, and every time I've done this with students, it's always been a right-skewed graph. They tend to get pennies that are kind of clumped, a lot of pennies that are pretty recent, and then only a few pennies that are maybe 50, 60 years old. So I would say it usually ends up being kind of a right-skewed kind of data, which I kind of like for this. You know what I'm saying, like getting data that wasn't exactly normal, as we might call it, or even approximately normal, like this is skewed right. So that's where we started, bringing all the data. And then what we did, after we took a picture of this, we actually messed up all these coins and randomized them as much as we could. And let me see. Here we go. And then they took each kid got a random sample of 5 pennies. So they randomly picked 5 pennies. And again, they looked at the year. So if it's 2018, that's a 1-year-old penny. And they took these ages, 10, 3, 1, 9, and 15 this person's got. They added them up, divided by 5 to find their average, and it was about 7.6 there. And so they each did that multiple times. And each time they did that, because I wanted them to get an idea of what they were building here. So I had them take a nickel. So these are actually nickels. I don't know why I said 7.8. It says 7.6. But each time they got a mean of their 5 pennies, they put a nickel on their on this table also for the age. So why did I? So Dan, what do you think about that? What do you think about that distribution there? This is called a sampling distribution of sample means. Can you talk about that and why that's a hard concept for your students to get if they're like my students?
I think what students like a whole distribution where they see each individual, each point on the graph represents one person, but this doesn't do that. This represents a group of 5 people. When I did it in class, I talked about heights, and so I talked about, okay, the starting 5 of a basketball team, and so that we were collecting heights of people, and we took our starting 5 of basketball teams, and we put them on Post-it notes, and we stuck them on the board to see what was our starting 5 going to look like. And so that was how we talked about it, but to understand that you're not talking about one person, but you're talking about the average height of 5 people. And I think that's a hard concept for students to understand and try to figure out what actually is happening.
Yeah, one of the reasons I like this activity is I could refer back to it later, so I could talk about, remember when we took the nickels, you know, and then after you do the nickels, you can do dimes, like 10 people, 10 pennies at a time. You can do quarters, 25 pennies at a time. And so, you know, that's it. By the way, interesting point. Someone who works for the Treasury, someone's friend did, and they said pennies are recycled every 10 years or so. So that's really interesting. Kind of tidbit of data there in the chat window. Feel free to add to the chat window as things go. And so this is the central limit theorem, which we were trying to, you know, talk about here. And in order to understand that, you have to understand that what the sampling distribution of the mean is. And so that's a, you know, whole bunch of means, like a whole bunch of nickels there, where they sampled and took the average and plotted that sampling distribution. And so as long as the data is independent, random, it will be normal or nearly normal if the sample size is large enough. I know we probably have some stat teachers out there. I'm curious what kinds of things we need to consider what's considered large enough. Like if you want to respond in the chat window, what kinds of things do we need to think about to make sure that our sample size there would be large enough? So if you want to respond in the chat window, you can do that. NP and NQ are greater than or equal to 10. So sometimes there's just like a generic rule we have for things. The sample should be random. 30, so 30 is kind of a big number. N is greater than or equal to 30, at least 30, but not exceeding 10%. I like that. You can tell some of these folks have taught stats before. If the population is nearly normal, any size should be okay. So that's a really astute question. It depends on what your population is. So if our population was normal, we could probably take 5 and it would be large enough. Don't you think, Diane? Do you agree with that?
It does work out that way pretty nicely. But the more skewed it is, the more you do have to take. And we do, in statistics, AP statistics, we do use this concept of N is equal to 30. I noticed one of the things with N times P being greater than or equal to 10, that's kind of dealing with proportions. And this question's not dealing with proportions as much as it's dealing with means. And so I think that's a statement my students often make. They want to tell me, you know, hey, it's N times P, and then we have to think about, well, what's P? And in this case, we don't have one. And then the 10% condition, that's a really interesting condition to talk with students about, is why is it important that our sample, that if we take our sample size and multiply it by 10, why does that have to be less than the size of our population? And it's an interesting thing to think about. I've actually done this with my class where we take part of them and use them as a sample and realize that one student can be used in every single sample several times. So therefore, our sample really is not random. And we often pass, so I know I used to pass over that all the time when I was teaching statistics because I'm not sure I understood it. And now realizing how important that 10% condition is if we're truly going to have a random sample.
Yeah, and you know, I probably, to tell you the truth with this activity, ideally you would shuffle them up. One kid would grab 5 pennies and then you'd randomize them again. I oftentimes would have them. There were so many pennies there that I just had them pick 5 each and keep refreshing them and mixing them before they picked again. But it does get, you know, you can be kind of a stickler there. And that is interesting. The AP rubrics don't always check the 10% condition, but it's still an interesting fact there. But so the central limit theorem has to do with that this thing will start being normal. And so even you can tell really with, to me, even with nickels, even though this is only a sample size of 5 here, you can see this population that's at least starting to be somewhat normal here. What other things do you notice about this grouping, the sampling distribution of the sample mean that we have here, Diane? Anything else that stands out to you besides it's not quite as skewed as the population was?
I think it's got less variance too. It's more
What do you mean by
squished
variance?
together.
Can you explain that?
Well, I think your last time you had a whole bunch at 1. Notice we don't have any at 1 this time. And you had a whole bunch out at 50. And there's nothing, I think that number might be, what, 33? Is your largest
33
one this
is
time.
about the biggest.
Yeah, so we have a smaller range, I guess is a pretty good way to say it. So the data is getting closer together.
You think about how tough it would be get something out near 50 here. So you'd have to pick randomly pick 5 pennies that happen to be really old pennies. I had to have my kids blindfold themselves because sometimes students would try to pick all new pennies or all old pennies. So they had to cover their eyes as they picked their pennies there. But yeah, that's always a concern that they could not randomly pick them because randomization is so important. And then just comparing them, you can see it a little bit better here. But even with this grouping of 5, the standard deviation is so much smaller here. But what do you notice when you compare the two? What else do you notice besides the sample, the standard deviation? The variation's a lot smaller. Is there one other thing you might notice here?
Well, yeah, we hope that they notice that the mean is about the same.
Yeah, and it's not perfect, and we only took a relatively small number of tries there, but oftentimes the sample mean, my experience is it's very, very close to that. That's actually a little bit further than I thought it might be, but the sampling of the population mean is 18.9, and then the sample mean is 16.7, so they're pretty close, but look at that, standard deviation is about cut in half there. So the precision, I mean, it's getting, so it's approaching normal, even with just 5. And the nickels, the dimes will get closer to that and so forth. So we wanted to go over a TI-Nspire document. And so what I did is I put all the data in here, the 1s, 2s, those are years there. I had to look this up, but if you hit Control-1, it goes to the bottom of the list. And so 53 is my latest year, and you hit Control-7, it goes to the top of the list, because there's over 350 pieces of data in that list. And so what we'd like to show you is a couple of commands that are native to the Nspire that you can actually do a sampling distribution with real data. So this is what we like is we collected the penny data. What I did, you can either use Navigator or if you want, collect the data one day and then the next day you have the data typed in. You can type it in to your calculator. And so I want to do a sample of this. Do you remember the name of the command here that we use for that, Diane?
I think you need to use ransample.
Ransamp. And you can see it kind of goes italicized, so you know it's a command. And so I want ransamp a penny, and that goes bold because it's a variable, comma, and let's pick 5 of those. So when I do that, it automatically randomly selects 5 of the 300 and some pennies that are out there in the population and grabs them. And over here, we can actually use a command like the mean of, let's call, it always helps to call that a name, doesn't it? Let's call that SAMP. And so equals and type in the mean of SAMP. So it should give me the mean of sample. So you add those up to 68, divide by 5. Diane, do you know how I could get that to be a decimal point? What do I need to do there?
I think you tell me. You have to put a prox in front of it.
Okay.
And that always helps students because they really don't like it when it's a fraction.
Yeah, they don't.
They're
so
anti-fraction.
It makes more sense to me too. So I like that. So that's our first. We grab 5 pennies using the calculator rather than actual pennies. But we're picking from the same population of pennies, and we found their mean here. And now I'd like to collect that data. So I think I need to somehow store that data here. So if I hit menu, let's see, if I right-click on it, variables, store variable. So I'm going to store that as, let's call that means, plural. You can't use the word mean, it's a command, but I could use means.
You also can get that by storing by hitting second in store if you can't remember the right click and all that stuff.
Oh, that'd be good. Yeah. And by the way, if you didn't know this, if you hit Control-R on your keypad there, Control-R, it'll randomly pick 5 more pennies in this case, and values, and it'll keep computing the average. So what we want to do is, as this average changes, we want to collect that data. So in the next column here, I'm going to call this plot. And I'm just going to, hit menu, data, and data capture here. We're going to do an automatic data capture of that variable. I think I called it means. And so it automatically captured 10.4. If I hit Control R to randomize, it captures anytime that number changes, that variable changes, it's going to capture that data piece. And wouldn't it be nice to see this as I capture a few more? Maybe you can see you can capture more here. But how could I watch this at the same time? What do you think, Diane?
Well, if you split the screen, that works well.
Okay.
Can you do a quick plot? So if you hit menu.
Okay, so menu is under data. There you go.
Yep.
Quick graph.
Yep.
And so you should be able to see as as long as my cursor is on the left here, if I hit Control R, it's going to plot more points every time I hit Control R. So it's adding to the list. You might have to adjust your scale just a little bit to make sure you can see all those values. Yeah, I couldn't see all those off to the right. Oh, wow, I had one at 37 or so there. And so you can add to that. You can just kind of see it as you change the sample means there. You're adding a penny or adding a nickel, I guess, so to speak, each time you do that. And of course, you could just change this if you wanted to. Instead of doing 5 at a time, we could change that command to do 10 or 20 or 25 at a time, and change and see how that would change the graph here by adding that. But I think it's kind of neat to work with real data. And again, so we're using the actual population, and we're basically recreating exactly what we did by hand, but you can see I can add those pennies really, really fast there. Just every time I hit Control R, it's going to add another nickel to our sampling distribution of the sample mean there.
So when I'm doing this in class, I sometimes if I have my navigator on and I have a navigator that I can work with, I assign different students in the class a different value for n, and then we can see the graph side by side so that they can see the difference between an n equals 5 and n equals 10. And then we get that discussion on what is large enough, and they can determine they make a guess in terms of what's large enough.
Oh, I really like that. So you saying, is 5 large enough? And when they see 5 and 10 and 25, and they see it compared to each other, oh, I really like that. So they're making the decision on what's large enough.
Yep.
Even though it's, oh, that's neat. I like that a lot. So the thing that I was impressed with, and I feel like it was kind of the highlight of my, tell me, how did you discover the, as we're kind of, I'm gonna trade this over to you, I think. Can you tell us how you, I know we were trying to do this at 84 and you were having a little trouble. How did you come about the realization that you could do this on the 84 that you're about to share with us?
Well, I was sitting in the airport and sitting next to another TIer, and we were discussing what I wanted to do, and he's an expert on the 84. And so David said to me, hey, let's try this. I explained him what we wanted to do. And so when as I spoke, he's like, I bet you we could write a program to do this. So I was fascinated by that, and so we then had to part ways because we both got on the airplane, and he had to sit in the back, and I was sitting in a different seat. And so I worked hard to see if I could get it to work between Dallas and Detroit, and somewhere up there in the middle, we got it to work. So I was quite excited. So the good or the interesting part is what we started with is I had actually typed the pennies in. Jeff sent me the data, and there it is in list L1.
Can you share your screen with us? I'm not seeing your screen.
Sorry. I'm sorry. I didn't do that.
You're okay.
Yeah. There, do you see it now?
Oh, I do.
No,
yeah.
That's not the one I want. Just a second here. There's my calculator. Why
Wait, so did you type this data in yourself then?
I typed them all in, every single one of them.
Yeah.
So there's my list in L1. So that's all the data. And so then I had to think about, okay, what did we want to do? Well, kind of what Jeff wanted to do is he wanted to pick 5. I'll show you the program in just a minute, but I'm going to explain here what these columns are, and then I'm going to show you how we wrote it. So what we wanted to do is we wanted to choose 5 pieces of data. And so in L2 are the 5 cells that the data is in. So that 247 is what number is in cell L1, 247. And so if I went down here to 247, I'm not going to get that far down, but I can show you 36 pretty quickly.
Yeah, show us 36. What's 36?
Yeah, so in 36, I have the number 2. So if I am over here, in cell 36, you can see I have the number 2. And so that's what's in L3. So in L3 is the value, so L2 basically is L1 of 247. And L3, so that's where L3 comes from. L3 is L2, L1 of 201. And so my
L2
values,
is just a randomly generated list of, can you explain what command you use to generate 5 random numbers from the list?
It's just a random numbers. I'll show you that in just a second. Then let me show you, so then in L4 is what it then did is in L3 it took the average of these numbers and it put it here in L4. So we had to kind of think about how we could get the calculator to do that. How can we do it with a program? And I'm not a great programmer. I've written very, very few programs, but I worked on writing this one. And so if I show you what it says, it starts out with this. So it's got 2 for loops, and 2 for loops are working inside of each other. So this outer for loop was repeating the experiment 30 times, kind of like Jeff kept hitting Command R to repeat 30 times. And so what it was going to do then is it in this second line, I knew I had 379 pennies, and so it's choosing the numbers 1 to 370 times. This is no repeat, so that's a special command that's fairly recent on the 84, that you can choose random numbers there, and then I put those in L2. And then
I really like that better than random integer. So random integer, no repeat, only picks, it will never repeat. So if it picks the 36th term, it won't pick the 36th term a second time.
Correct. And so that was really important. The first time I wrote it, I didn't write it with a random int. I just do the random int, and I got some data that wasn't quite what I was expecting it to be because it could use 33 twice or something like that could happen twice. And if it happened to choose number 379 twice, my data was really, it was kind of bizarre. So then I found the no repeat. There's my list. That's the numbers in L2. Then here's my second loop. And my second loop was taking those numbers from the ones out of L1 and choosing those and putting those 5 numbers in L3. And then what I wanted them to do with the L3, I wanted to find the mean of those. And then I wanted it to store it in L4 of I. So therefore, in L4, I have 30 pieces of data, and each of those is a mean of 5 numbers that have been randomly generated in those other 2 lists.
Wait, so this is the whole program? It's just
that's
this long?
The whole program.
Wow, that's pretty economical.
Yeah, so things I could change. If I wanted to have more than 30 samples, I would have to change the 30 up here. If I wanted to do Jeff's problem, like instead of having nickels to use dimes, I would have to change this 5 to the 10. And other than that, everything else can, and if I was going to change this 5 and this 5 have to be the same number. So if this has to be a 10, then this would need to be a 10. So then, so that's kind of the program. So let me get back here. I'll run it for you again. What I actually, whoops, that's not what I wanted to do. I got to have a program here. It's kind of interesting. It doesn't, you notice that's how fast it is, which I was fascinated by. And now if I go back to my stat and if I look at that data again, there's a different set of numbers than what I had before, because you remember I had a 36 in here before. And then, so I wanted to set the stat plot up. So if you remember how to set the stat plot up, we're going to turn it on. I'm going to go down. I know my data is in L4. So there's my L4. I'm going to save myself a step and hit Zoom 9. Look at that.
You know, I just want to tell you, we had Patrick Wheels suggested you could add a command at the beginning of the program to ask users to select the sample size.
Yes.
I didn't even think about that, but you could.
Oh, yeah. Well, there's lots of things I think we could do to the program. This, you have to understand, is probably the
right.
I haven't written many programs doing this.
Yeah, that's interesting. I just
but
thought that was a neat idea to share.
Yeah, I was really excited that it worked so nicely. I was thrilled to death. So.
Yeah. I like that. Oh, so this is the sampling distribution. So that looks.
That is.
Approximately normal.
It does look approximately normal.
Can you tell where the mean is on that?
I got to remember how to do that. I have to calculate the mean. I could calculate the mean of L4 to be able to do it. But I can't plot it. I can't plot a mean quite the same way.
Oh, yeah. Okay.
Okay. So, hey, can I show you something else?
Yes.
If we can shift to a program that's written by Texas Instruments. So when you first told me this, Jeff, I was like, I told you I've done this before. So there's this is a pre-written document by Texas Instruments. It is called the Central Limit Theorem related properties. It's kind of a cool one. It allows students to build different distributions based on some characteristics. So like you have to do with most things, because if you don't do this, every student in your class gets the exact same results. My favorite's when they copy my number.
That's funny. I always have them put the last 4 digits of their phone number. Is that what you do? You do something else?
No, I just tell them to type any 4 digits and don't do the same numbers that I'm doing.
Okay.
And I choose different numbers every single time.
It doesn't have to be 4. It could be any number there.
Yeah, I always do 4 digits. It's gotten routine. So this first distribution it plays around with is the set of digits. And so if you had 10 digits and you have 100 digits, you expect your population, you have 10 of every single one of them. So you have a very, very uniform distribution. And so in your uniform,
you mean flat on the top. So the distribution is completely uniform and flat there.
It is.
And what's this down on the bottom? What is this here?
This is first, this is n equals 1. So this is if I go in and I choose, and I do this 200 times, and I choose a number out of this hat. Because in this hat I had 10 10s and 10 1s and 10 2s and 10 3s and 10 4s. And I just pick one randomly, I get this. So the cool part is, again, if I'm using the navigator, students can all see that everybody's is different and that they're not all uniform.
But, I mean, they're not really normal or skewed right. It's just kind of,
Yep, it's just
somewhat
sort of there.
uniform. It's somewhat
but they're not uniform, which is kind of interesting. And so then if it got really excited, didn't it?
Wow. You went
there. So if n is 2, look what happened that quickly.
It's already starting to, because I guess when you pick 2 numbers, if you think about that, so you randomly pick 2 numbers, maybe a 1 and a 6, the mean of those 2 numbers might be 3.5, and so you tend to get numbers more in the middle here because you're averaging 2 numbers. Each one of these data points here is the average of 2 numbers, right?
Yeah, and that's really important to spend time with students and allow them to think about what you're actually doing. I actually do it in class that we pick out 2 numbers and we look at them and then we average them together, because sometimes it takes us a little while to figure out why are we getting a 2.5? Like what is actually taking place there? And so I do think it's important to spend a little bit of time and talk about what's taking place so that they understand the distribution of what's happening. And so we talk about how unusual it is to get a 0, because the only way to get a 0 would be to draw 2 zeros out. And then the only way to get a 9 is to draw 2 9s out. And so that's probably pretty unusual. But we talk about how many ways you can get a 5.
Yeah, I really think starting with real stuff, like you're saying, can really be the key for them to get some student understanding into this. But this goes further than that, because then you can jump it up to
so let's go here. So there's n equals 5. There's n equals 10. There's n equals 15.
What's that line down there, like on the bottom there? There's a line I see.
This is the normal distribution.
Oh, okay.
So that's what a normal distribution would look like. So it's an interesting thing. So a question that I typically talk with students is we talk about, well, what's the range of values here? What's the range of values? What's happening to the range of values? And usually we're also talking standard deviation as we're doing it, and they can see, hey, the standard deviation is getting smaller. How much smaller? It's always an interesting concept to talk about. And so we continue to build it. We can get up to n equals 30 here. It's pretty normal with n equals 30.
Wow.
when we
It's
started
almost
with a
like
pretty
you
normal
planned that. I mean, that was, and this is random. Every time you click that, it gets a little different. It's randomly calculating this every time.
Yeah.
I notice it changes every time.
It does, and it's really cool if you can, if students can see each other somehow. Sometimes they lean over, look at them, but so that they can see that everyone's is different.
Yeah.
So that's kind of a cool one. That's a uniform population. So the next one they have here is its heights of people. And again, so you have the same thing here. Here you have a distribution of heights. You can talk about what the distribution looks like. It probably starts out looking, my students would probably say that's pretty normal.
Yeah.
And then when we start, so now what we did down here is we chose one person. And we did it 200 times, and we plotted their height.
That's not bad, actually, because the population's somewhat normal. The sampling distribution, even with size 1, is somewhat normal there.
It's pretty normal, yep. And again, they can continue to build it, because the other thing we want them to understand while doing sampling distributions is the mean stays the same, but the standard deviation begins to get smaller. And we really want them to understand that, because those are two really big points that come along with the central limit theorem. So here I go if n equals 2, and you can see what's going to continue to happen. That was pretty normal by n equals 5. And most would say that, we probably need, with that, n is large enough with 5 there.
Wow.
Okay. Yeah. So here's the next one. There's your, this is your pennies.
Yeah. This
So
looks a lot like my data.
Yep. It looks like your data, and this is their pennies. And so again, this data is extremely skewed to the right.
And look at the sampling distribution is also almost looks like a carbon copy of the population.
Yep. Yep. And that's when n was 1. But again, we can do the same thing. We can, we had this discussion in class. How many is large enough here for us? Well, 2, that doesn't look very normal. 5, that's okay, but it's not wonderful. There's 10. That's pretty
not
good.
too bad.
Yeah, not bad at all.
Yeah, I mean, in stats, it's such a different kind of math because it's not a perfect world. It's not like any of these are going to be completely perfectly normal.
Yep.
There's always some variation when you're dealing with real data here. There's always that variation. You just have to kind of get used to that when you teach stats.
Right, and that there's no one solid right answer that's right all the time. It's not black and white like calculus often can be black and white, or algebra when you factor and solve an equation it's got 2 answers and that's all it's going to get. Statistics is a little harder for students because there are so many variations in it, and what my graph looks like may not be what my neighbor's graph looks like. And that's a difficult concept for students to understand who like things very, very black and white because it's math class.
But the mean of that is pretty similar to the mean of that population. One way I've learned for the population, if you kind of put your cursor where the balancing point is on that plot, I don't know, it looks like it's around 12 or so, like the balancing point. Does that make sense when I say the balancing point? That's where you can estimate the mean by doing that. And it looks like the mean is about a pretty similar spot there. So the means are pretty, but the standard deviation is so much smaller with the sampling distribution.
Yep.
And the shape is so much different. So that central limit theorem, you can really see it in action here. I think especially when you have a population that's not normal. I think it's one of the surprising things in stats is that even when the population isn't normal, as long as the sample size is large enough, it starts looking approximately normal.
Yeah, and this is where it's really important to build this background for sampling distribution so that when you start teaching hypothesis testing or building confidence intervals, they can understand that as long as n is large enough, we can use, the whole goal is to be able to use this sampling distribution to draw a conclusion about our population. And without some of these things, so if you don't understand the backwards part of it, like, hey, this is what's going to happen, this is what does happen, hey, isn't that pretty cool, it makes hypothesis testing really, really difficult for students to understand.
No doubt. What's the next page have?
Here, this is the weirdest one ever. So this is rolling a die. It's a binomial distribution, and you're rolling a 2. So if you get a 2, it's this 1 here. And this over here is if you don't get a 2. And so this,
the probability of not getting a 2 would be 5/6.
Yep.
The probability of getting a 2 would be 1/6.
Yep. And
so
so
success and fail, but it's not it's not an equal kind of thing. Oh wow! And so you took a sample of size 1, and you got you happened to get you rolled what you wanted to roll there.
Yeah. So this was kind of interesting to watch, and this one was the hardest one for my students to understand. So we actually did it. We rolled the die in class. We had already talked about binomial distribution, so they understood it. But this took a little bit to get. But watch what happens here. Even with a binomial distribution, if n gets large enough, look what happens.
Yeah.
530.
Dan, can you? I have a question for you, just from the chat window. How do you store the mean of the sample to get the sampling distribution on the TI-84?
Ask that question one more time.
How do you store the mean of the sample to get the sampling mean distribution on the?
Back here.
How did you store it? Yeah.
How did I store it? It was this line right down here.
Maybe they were talking about TI-Nspire. Maybe Aaron was talking about TI-Nspire.
So if I want the mean of any of these distributions, it's kind of, if I want the mean of this one up here, if I go over here and hit menu, and if I hit analyze, and I hit plot value, I would like to hit the mean. Ooh, I don't know what this one's called. I hope it's age. Ooh, I got a lucky one. Mean of age, and there it is.
Wow.
So now what I don't, that looks a little off to me.
No, that looks way off.
Yeah. So I'd have to look and see what their age data actually was. But in general, that will work. You can put a vertical line. You can do it for the mean. I bet you on yours it would work.
I think maybe she was talking about the right click that I did on that cell. So if you don't click on the cell and right click, and then you can go to variables and store variable. I bet that's what it was.
Okay.
I thought she was talking about TI-84 there for a second. Aaron was. Okay.
Hey, so do you want to, so that's the cool activity. So this one's already pre-written. You can get it off of the Activities Exchange. It is there. It's in Math-Inspired, but it's a pretty cool one.
Yeah. Can you show us where that's at real quick? Would that take long? Do you have your internet up?
What do you want me to do?
Just show me where that is on education.ti.com. Can you just go to that website for a second, or no? If you can, it's okay.
It'll probably take me too long to get there. And then you'd see all my other things open. How about I toss it over to you? Are you going to work on, we're going to try that one problem with the AP?
Okay, so yeah, you can toss it to me, and I'll show that website, and then I can toss it back to you. That'll work?
Okay.
Let's see. Oh, I see it now.
I think you're there.
Okay. Share screen. Okay, so this is the education.ti.com website. And if you go to professional activities, here it is, under Math-Inspired. I just want to show you that there are activities for many different subjects here. And I like that you can go to stats here. I've used lots of these in my AP stats class, or even with my Algebra 2 students. And so that would be sampling probably, my guess. And let's see if it was sampling. Now let's see, maybe it was sampling distribution. That's what it is. So when you click on that, here's the choice for Central Limit Theorem. This is the activity that we saw there. And so you can actually just go to, you can get a student activity. You can get the teacher notes, which gives you the background materials for this. You can download the actual calculator file for TI-Nspire there as well. And in addition, by the way, if you look at some of the activities we've given you, the one that I did in my class with the penny activity, we're giving you this activity as well. So this is just what I had students fill out in class, and questions for them to ask, and so forth. So we're giving you some of that activity as well. So you have some resources to share. I'm going to pass it back to you, Diane. Can you share your screen again? We're getting good at this.
Yep.
All right.
So we're going to look at our other
Now, you had an AP question for it.
I did.
Right?
I did. So this is from 2009. So it was interesting when we were talking about this because I actually did this 2 weeks ago in class. So you have a tire manufacturer desired a new tread pattern for its all-weather tires. Repeated trials were conducted, cars the same weight, traveling 60 miles per hour. It shows you that their average ability to stop is 125 feet with a standard deviation of 6.5, and that the stopping distance are approximately normally distributed. So first question says, what's the 70th percentile of the distributions of stopping distances? So I like this question because it provided a variety of different things for us to think about. And the first thing it asks us to think about, what is the 70th percentile? So I've shown two different ways for us to solve this one, both using the Nspire and using the 84. So with the Nspire, these things, let me get a new document here. Realizing that what we're looking for is that we are looking for, we know the area under the curve. We know the area under the curve. We're looking for a 70th percentile, so the area under the curve is 0.7. And we know what our mean and standard deviation is. So my students, we have a discussion frequently, you know, what class are we sitting? Well, we're in statistics. What are we trying to deal with? We're dealing with a distribution, and what do we want to do? Well, we want to go backwards. So if we want to go backwards, we're looking for the inverse.
I like that,
so it always makes me think about the area. I stress throughout most of the beginning of the year that the area under the curve has to be 1, so therefore the 70th percentile has to have an area of 0.70. We knew our mean was 125, and we knew our standard deviation was 6.5. And this will give us what our 70th percentile is.
Yeah.
So 70% of all cars will stop at 128.4 feet or less. If you want to do this on the 84, all of its distributions are found up here with a second command. So if you hit second in distributions, it again is inverse norm. The area is 0.7.
Oh, I like that there's a wizard for this. This is called a wizard?
Yep.
I really like that it has that.
Yep, it's easier than typing it in with commas and not remembering which one.
You don't have to remember the syntax for the command.
Correct. Now you have to turn the stat. It's important you have to turn the stat wizards on. There is in your mode you can have stat wizards on or stat wizards off. I would highly recommend that you turn stat wizards on always, because if not, it's really hard. But that's something that a lot of people don't know.
Can you explain to me what this means, left, center, and right? Because the 84 gives this option here.
Yeah, I keep having to think about why it does. So the left is the tail we're interested, because we're doing the tail to the left. We want our 70% to be to the left. That's what a 70th percentile is. The center is going to give me my middle 70%. So when I'm talking about confidence intervals, this will give me my confidence interval in the center if I would like it to be. And the right will give me technically it gives me my 30th percentile.
That's like your 30th percentile. I got you. I got you.
It is. So I stick with the left. I'm going to paste it in. I have to hit enter. And there's that exact same number. Yeah. Okay.
And is there a part B of this question? Lots of times on the AP.
Oh, yeah. There's a part B and a part C. Oh, I have to go back to it. So here is, that's my first part. Part B of the question says, what is the probability that at least 2 out of the 5 cars will stop at a distance that is greater than the distance we calculated? So we have to think about what it means, what's the probability that's greater. So therefore, in this case, it's a binomial distribution. We know that n is 5. But what is p this time?
Yeah, because binomial has a set number of trials, right?
Yeah, so that's 5.
And it's saying at least 2. So it's not just 2 out of 5, but at least 2. So it's not PDF, but a CDF kind of command there.
It is. But what is P? Like, what's our probability of success?
So that's a good question.
We want to stop at a distance that's greater, so our probability of success this time is 0.3.
Oh, yeah. That makes sense.
Okay, and so let me walk through both of these, because both of these have they're slightly different solutions. So the first one.
These are, so if you haven't seen this, these are a difference between the 84 and Nspire. When you do binomial CDF, I think this is one of the biggest difference in stats as far as the way the commands work. Don't you agree?
I would agree completely. And it took me a long time. I was tutoring a student, and I didn't know it was doing this, and I couldn't figure out why the 84 was getting different answers. So it took me a while to figure it out. So binomial, this is a binomial CDF because we're going to add up a bunch of things. We know our trials is 5. Our success is 0.3. This case, our lower bound is 2, and our upper bound is 5. Because we want
to I like the way that works.
Yep, it looks pretty nice. And then we click OK, and we get our nice little answer there. The challenge is the 84, and you have to understand what the 84 is doing. So again, it's a distribution, and it's a binomial distribution. Now we don't see it, but if we go from the bottom, we can find it. So there's my binomial distribution.
Can you hit plus there? Don't hit B yet. Can you hit plus? What's it tell you when you hit plus? It says number of trials, PX. Okay, I was just wondering.
Yep.
You can get rid of that. I'm sorry.
Yep. Yep. So there's so my binomial CDF there. So this will give me, here's my same type of thing.
Anyway. Yeah.
Right, because we have the wizards on. So I have 5 trials. I have P to be 0.3, but here's the difference. When you're doing the binomial CDF, it counts from the left up to, it starts at 0. And so in this case, we cannot go from 2 to 5. So what we have to do in this case instead is we have to find it for 0 and 1 and realize the answer is going to be 1 minus that. Because if I can be 0, 1, 2, 3, 4, and 5, and I want to be greater than 2, greater than or equal to 2, I can't be 0 and 1. So here my x value is going to be 1.
What's that called? Is it like the complement? What's the stat word for that? Is it the complement? When you do 1 minus the probability.
Yeah, I think you're right there. So
something like that.
Right. So we do that, so you can see we don't get the same answer, but if I take 1 minus and grab that answer, we get it. And so it's important that students understand what their calculator is doing so that when they're calculating and what some of these commands happen to mean. The last part of the question, there's a third part, which is why we were getting to this one. The third part of the question says,
third part,
yep, what is the probability that a randomly selected sample of 5 cars has a mean stopping distance that's at least 130 feet? So this is a sampling distribution. Because we're taking 5 cars and we want to know their mean stopping distance. So we're going to do the same type, but we're going to find those commands in similar places.
And this is the big one. Don't you think that we use this command all the time?
Oh, this comes up a lot. This is normal CDF.
Norm CDF, that bad boy, okay.
Yep.
We use that all the time.
Yep. Here my lower bound's 130. My upper bound's a big number. My mean is 125. But here's where we're really dealing with a sampling distribution. So the other thing we know about a sampling distribution is that our standard deviation is the standard deviation of the population divided by the square root of n. And this is part of the Central Limit Theorem, and that's why our standard deviations are getting smaller and smaller and smaller. And if you notice when Jeff did his problem before, Jeff said that his standard deviation without those nickels with the pennies was about half. And the reason it was about half is because the square root of 5 is a little bit more than 2.
Wait, did you stop there? Oh, I wanted you to stop there just for a second. Talk about 2 things. One is, first of all, I think it's really neat that you can type in 6.5 divided by square root of 5 there.
Oh, yeah, I think so too.
And the other thing Tom Marshall said is that if you have a CAS calculator like you have right now, you can choose positive infinity there.
Oh,
but if you don't have a CAS calculator, you just have to put in a big number.
Yep.
So that's the difference there. So if you have a CAS calculator, you can put in infinity there, but if you don't. But I love that you can actually type in 6.5 divided by square root of 5.
And my students and I have a discussion about this upper bound and what is important with the upper bound. I mean, would I get the same answer if I did an upper bound of 1,000? The answer is yes. If I did an upper bound of 500, would I get the exact answer? The answer is yes. And so, because I think it's important for them to understand, what happens, what are those probabilities as I get over to the tail? And those probabilities I get to the tail are so very, very small that basically we're adding basically next to nothing. And so it doesn't matter. So if you
Yeah.
put 1,000 in here, or if you put, 500 in here, you'll be fine both ways. But I think
Yeah.
it's a really good discussion for them to understand what you're actually doing.
Yeah. So let's see that on the 84 before we sign off here.
84 does the same thing. If we hit second in distributions, normal distributions, remember, keep that stat wizard on. So here my lower bound, again, was 130. My upper bound here, I'll make it smaller for you. I'll make it only 1,000. Again,
Okay.
my standard is 125.
And you can do this even in the 84, because I really
Yes,
like
you
what you're
can.
doing there. I mean, from a teaching perspective, writing it like that, it's really nice.
It is, and it makes sure that they understand versus approximating one more thing that they're copying from somewhere.
Patrick says he always puts 10 to the 99th power in there. That's a pretty big number.
Yeah. They always don't get what that E to the 99. I had a question the other day on a test. The answer came out E times 10 to, or
Right.
came E negative 23, and they all wrote it out for me.
Think go big or go home, he says.
Yep.
That's funny.
Yep. Yeah. So that's, I think, our last question.
I think that was. I think I feel like I learned some stuff. And I just really am excited the fact that you can do that penny activity on the 84. I mean, the fact that you were able to show us that was just, that was groundbreaking to me. And that program was only a few lines long. And did we provide, last question, did we provide that program to the participants?
Well, I gave the program to Mike, so that's Mike's job now. I gave,
okay.
The program's been written, and Mike has that, and he also has the data. So if you guys don't want to type in 379 pieces of data, you can use the data that I provided.
Right, that's right. We've done crazier things as teachers than type in that many pieces of data.
Yep, it was nice. I was
really
on an
enjoyed
airplane
this.
doing it.
Yeah, I'm going to give the ball to Mike here.
Okay.
Or can you do that? Can you get
I'm
that
working
control?
on it. Yep. Oh, I got to go back up here. I'm getting close. There you go, Mike.
Thanks so much, Diane and Jeff, for everything you shared tonight. We do have a couple minutes left, and as we begin wrapping things up, if you have any last-minute questions, please feel free to try and get those asked. I know Diane and Jeff will try to get those answered, even though we only have about 2 minutes left.
The OS I was using is 5.3. It's the most recent operating system for the 84. I strongly suggest you download it if you have it. If you haven't done that, it's got some other really, really cool things on it.
Thanks, Diane. We're really excited that the T-Cubed International Conference is coming up. Seems just like a few days away. March 2nd to the 4th in San Antonio, Texas. I'm pretty sure that both Diane and Jeff are going to be there, and there's even a chance that they'll probably be presenting some sessions as well. So please feel free to join us at the T-Cubed International Conference. I've been saying for many weeks now that I feel like it's the best professional development that I've ever attended. I just really love connecting with people like Jeff and Diane and actually getting the chance to pick their brain and just sit down and talk to them for a few minutes. Jeff, anything else you want to add to that?
No, I think I really enjoyed the back and forth with the participants as well, and the idea, the changing the program idea. It's great when people. I just love learning. It's a great time. I really enjoyed it today.
Thanks.
Yeah, thanks for all coming out tonight.
Well, we're excited that tonight we're giving away to one lucky winner a registration for 2 to the T-Cubed International Conference coming up, and tonight's lucky winner is Zioya Che. So Zioya, congratulations. Really hope to see you as well as everyone else at the T-Cubed International Conference coming up really, really soon. Visit our website to learn more and register.
Yeah, I'd love to meet you there. I'm actually doing something on stats on the 84 while I'm there.
Thanks, Diane. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents, so you don't have to type in 300+ entry lines by hand. Thanks, Diane, for doing that for us. If you happen to miss these links or if they're not working for you, have no fear. You'll automatically get a follow-up email in a couple days. In that follow-up email will be a link to the recording, a link to the certificate, and a link to the documents. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. So,
yeah, Mike, there was a question. Did you use RANSAMP to choose the participant who wins, or is it RANSAMPLE no repeat?
RANSAMP no repeats. Thanks, Jeff. So thanks, Jeff and Diane, for everything you shared tonight. I agree with Jeff. I always like learning, and tonight I learned a few things. I wasn't aware of the power of the 84, so I'm excited to have learned that tonight. So thanks so much for everything you both shared.
You're welcome.
Hey, it was fun.
Thanks again, everyone, and we hope to see you back online real soon. Have a great night.